Hello, dear students. So we're done with chapter 6 and now we're moving to chapter 9 where we're going to cover 4 sections out of chapter 9, 9.1, 9.2 and then 9.4, 9.5. The first 2 sections are all about parametric equations and the other 2 about polar coordinates. Today we're going to cover section 9.1 about the plane, curves and parametric equations. So firstly, we need to understand what do we mean by parametric equations. This is one of the very important topics. You'll notice, I don't know if you heard about this before, but I'm confident that you've heard about the parametric equations in your physics courses. It has many different applications. We use the idea of the parametric equations. We use it in physics and motion. We use it in engineering and design, in mathematics for sure, and its application like vector calculus, complex curves. Even with computer graphics and animation, we use the parametric equations, astronomy, many different fields, we use the parametric equations. Now, to understand the parametric equations, we need just to think about our original function that we know, which is the mapping f of x takes x to y. And we say usually that f of x equals to y. Now, for these x and y that we know them in our previous studying, we'll have from now on, we'll use x as a function of t. T is the parameter. Usually they use it to represent the time. And y equals y of t. So our both variables x and y, they are now functions of t. And these two equations, x equals x of t, y equals y of t, is what we call parametric equations. Now, if we take these points, okay, x, y, so we're changing time. According to the change of time, the values for x and y will change accordingly. So if I take list of these points and I try to plot them into the xy plane, I'll get a graph, okay, where these two x of t and y of t, both of them are continuous function. Notice that both of these two are continuous function, and d is the interval of the real line. The graph that we'll represent here, that we're graphing, we'll call it the plane curve. Okay, so the graph that we have it using the parametric equations, we'll call it the plane curve. Now, how do we graph these plane curves? There's 2 methods. The first method, we'll see it in this example. So let's say that this is method number 1. Now, what's the question? In this example 1.1, it says sketch the plane curve defined by the parametric equation. So they give us 2 parametric equations. X equals 6 minus t squared, y equals t over 2, where t is between -2 and 4. So they give us like restricted domain. T is changing between -2 and 4. The first method, which you already know just in graphing, the basic method we usually use is just creating a table of ordered pairs, and then we plot them into the xy coordinates and we'll see what will be the graph. How do we create our table? Notice that we have the values for t, which is changes from -2 to 4. So if I start with integers, I'll take -2, -1, 0, 1, 2, 3, 4. That's it. So t goes from -2 to 4. Now, how can I find x? Just only like substitute the values for t in the equation of x. Same for y. Replace them in the equation of y. If I do the substitution, I'll create this table. So if t is equal to -2, just try to replace here 6 minus -2 squared, this is equals to 2. If I replace in y, this is equals to -1. And I'll continue creating our table. This is -half. At 0, this is 6, 0. This is 5, half, 2, 1. And I have at 3, -3, 3 over 2. And lastly, at 4, x is equal to -10 and y equals to 2. Notice these xy are basically our xy coordinates, an order pair. If I need to plug this order pair over here, let's just do our scale. I'll take, since we have -10, I'll use the scale of 2, 4, 6, 8, down -4, -2, -4, -6, -8, -10, and the y-axis I'll make it only a scale normal, like 1, 2. So this is 1, 2, 3. Okay, now see the points. Let's plot these points. The first point, we have 2, -1. So notice this is a restricted domain. So it has starting point and end point. 2, -1, let's say this is our starting point. And then we have 5, -½ somewhere here. And then we have 6, 0, it's here. And then we have 5½ over there. And then we have 2, 1, it's here. And -3, 3 over 2, somewhere here. And then lastly, I have -10, 2. Okay, so these are our points. If I join them, okay, I'll join them with our curve. So it will be something like this. This is our starting point and this is our end point. If I look or follow the direction where we're moving here, clearly that we're moving in this direction, right? Moving from this side to this side. This is the direction we're using. And this direction is what we call the orientation for this curve. This is these green arrows, this is what we call the orientation. The orientation here, okay, of the curve. So it shows the direction as t increases, what will happen, okay? So as t increases, what will happen to the graph, the direction of the movement or the path we're having. So what I want you to think here, just as a parametric equation, it's good to think about it that you have an object which changes its location, okay, with respect to time. So we start with here, after like, let's say 1 minute, we move to there, 2 minutes to there. So this is the direction and we track the location of that object as t changes from -2 to 4. Another method we can use, which is we're going to use in the next few examples, this second method. So first method, which is a table, you know, this is basic method for graphing. The second method, it's just the idea of the second method is to eliminate t, okay? So imagine that we eliminate t, so we end up with a function in terms of x and y only, which is the familiar one, the one you know, f of x equals to y. So the second method here, this is method number 2. So the first method, we've used a table. In the second method, we have to use the elimination, okay? I need to eliminate, I have to eliminate the parameter t. The parameter t. Okay, how can I eliminate t? Okay, let's check. The two equations we have over here, I have x equals 6 minus t squared and y equals t over 2. These two equations. Now from the second equation, if I solve it with respect to t in equation 2, so t will be equals to 2y. Now, if I plug this into equation number 1, okay, so I need to substitute t equals to 2y in, let's call this equation 1. In equation 1, what we're going to get is this. X equals 6 minus t squared. Remember, anytime you replace or you do substitution, keep the brackets just so that you don't do any mistake. So this is 6 minus 4t squared. Sorry, we need to replace with y. So this is 2y and this is 4y squared. So basically our function now is x equals 6 minus 4y squared, which is a parabola opened to the left. This is a parabola open to the left. This is a parabola open to the left. Opening to the left. If I need to check the values, the points here, so I need to change t from -2 to 4. Now maybe you'll ask, okay, if I know this parabola on how to graph it, I need at least the starting point and the end point, just to know how do we graph this function. And if you need to check the orientation with these types of questions, if you did use the elimination method and you eliminate t, and then maybe you ask, okay, I know how to graph this parabola. Okay, I know that this is 2, -1. I'll start from here. Then I'll move to 6, 0. Let's say I have 6, 0. Then we move over there. And then we have the point of -3, 1.5. And then lastly, we have -2, -4, 6, 8, 10. It was -10, 2, somewhere here. So if I graph the parabola, I'm just trying to be a bit accurate. So this is our parabola. It's open to the left, starting at this point to -1, and we end at 10 or -10, 2. Okay, I need the intercept. Usually it's important when you graph to know the intercept. So I have 6, 0, okay, the x-intercept. Now, if I need to know the orientation for this curve when I graph it, the easiest way to follow the orientation is just by taking any 2 points to track the direction of the t and xy, what will happen. So as t increases, let's say that t starts from -2, I need only 2 points, enough. -1. So here you need to check the point xy. Only you need 2 points in that case. Just to be sure just what's the orientation. This is the easiest way. So this is like 2, -1. 2, -1, and this is 5, -. Okay, so I know that the direction is this way. Okay, so the second method, just by eliminating the parameter t, I eliminate it. Now I have the equation in terms of x and y only, which you should know how to graph it. This is a parabola open to the left. So we graph the parabola, but you need to take into consideration, this is not the parabola in general. This is a parabola with restricted domain. So we have like x changes only from 2. We have x from 2 till we're moving till the point -10, 2. To know the orientation in that case, once you know the graph, you need to check the orientation. The easiest way, once we don't need just to do every time the table for all of the points, just check 2 points and track the movement. It's going which way. Okay, just to know the orientation, we need to check at least 2 points. Now let's move to another example. This is the graph. Okay, so it's showing you just the graph for the first function. This is 1.1. Now we'll move to question 1.3. In example 1.3, we need to sketch the plane curves defined by the parametric equations x equals 2 cosine of t, y equals 2 sine of t. Now in any question, once you see sine and cosine, I'm not going to use the table method, okay? So from now on, we'll use the elimination method. So I need to eliminate t. And this time they give me the domain of t from 0 to 2 pi. Now to eliminate t, the only way to get rid of t is just to use the Pythagorean identity. So the idea here is just to use the identity of sine squared plus cosine squared equal to 1. So I'll use this trig identity. So I need to use sine squared of t plus cosine squared of t equals to 1. Notice here in our original equation, I need to solve for cosine, I need to solve for sine. So sine is equal to what? Sine of t, it's y over 2. And cosine of t, it's x over 2. Okay, I'll use these two. So now we'll have, so we know what's cosine and we know what's sine. Now we need to just replace them. So now we need to plug sine squared plus cosine squared t equals to 1. Sine squared, it's y squared over 4 plus cosine squared, it's x squared over 4 equals to 1. And now this should be one of the famous equations that you should know. I could rewrite it using this way. If you multiply the whole equation by 4, this is x squared plus y squared equals to 4. And this is the equation of a circle. This is a circle equation. Okay, so this is a circle equation with radius of 2 and centered at the origin. Remember the general form of the circle equation. The circle equation in general, it says x minus a squared plus y minus b squared equals r squared, where r is the radius and the point AB is the center. Okay, this is the general form of the circle equation. So this one is a special case. There's nothing around x squared, y squared, which means that the center is 0, 0, the origin. And the radius here, r squared, is 4, so r is equal to 2. Now, if I need to plug in or to graph the circle, it's very simple. So we'll start with the points here. The center is 0, 0, and the radius is 2. So just you move 2 steps to here, 2 up, 2 to the left, and 2 down. Okay? Now, I need to see the direction. From where do I move? Where do we need to go? We know the 4 points. This is what shows the circle, but I need to know the orientation. We're going from where to where? As I said before, the easiest way to see the orientation, just use any 2 points on that table. We have the points here from 0 to 2 pi. So let's say that we took these 2 points. So let's say we started from t equals to, this is xy. So if t is equals to 0, and then we take pi over 2. So if t is equals to 0, check now. Cosine 0 is 1 times 2, 2. So x is equal to 2. When t is equals to 0, y is 0. So the first point is 2, 0. Now at pi over 2, cosine pi over 2, 0 times 2, this is 0. Sine pi over 2, 1 times 2, this is 2. So that means we start with 2, 0, okay? This is 2, 0. And we move to 0, 2. So this is this direction. So we're moving counterclockwise. This is what creates our circle. Let's show the orientation using another color. So we started from here to there, to here, to there. So the orientation here is counterclockwise. Counterclockwise. Okay. So anytime you see any question involves sine and cosine, you need to think to use the trig identity, Pythagorean identity. So we write the identity, sine squared plus cosine squared equals to 1. Try to solve these two equations for sine and cosine. Okay, so this is now the equation. It should be something familiar, you know. This is the equation of a circle. Radius 2, center at the origin. Remember, this is the general form of the circle. Sometimes if we change the center A and B. But notice the original formula has negative. So if we say, like, for example, x plus 2 squared plus y plus 3 squared equals to 9. This is a circle of radius 3 and the center will be -2, -3. Okay? Notice the general rule has negative sign. So if it's positive, that means the point is negative, just in case, if you have any other case. Now this is part A. So we need the interval from 0 to 2 pi. Notice here that from 0 to 2 pi, we finish just one full revolution. So we start from here, we continue up to 2 pi, so we close the circle. So we have a whole circle, one revolution from 0 to 2 pi. Now part B, for the same question, they tell me to graph it or sketch the plane curve for the same parametric equations, but the only change here is the interval. In part A, it was from 0 to 2 pi. Part B, it's only from 0 to pi, which should be simple for you. If it's from only 0 to 2 pi, so it's still exactly the same equation as before. Just check what we've done in part A. So this is still x squared plus y squared equals to 4. But in this case, we use only from 0 to pi. So it's again a circle, but we'll take only semicircle, half of this circle. Okay, so I'll take it with the same orientation, but we'll take only semicircle, the top part. We're moving to here and then down to there and then we stop. So this is only a semicircle. This is a top semicircle. Same thing. The center is the origin and the radius is equal to 2. So you see, when I graph it, I always start with the origin. What's the radius 2? I move right, left, up, down, whatever the part I need. Let's say we have for the same question, but I give you the domain from 0 to 3 pi over 2. So it will be like, if it's up to 3 pi over 2, I'll continue to here and then I'll continue to 3 pi over 2. It will be like this, 3/4 of a circle. So that's why you need always to keep your eye on the restricted domain, the given domain in the question, just to know which part you need to graph. Now let's move to one additional question. Now what I need to help you just with, before we graph, we need to check, make our guessing, what will be the graph. Now to get a circle, we need always the coefficient for sine and cosine to be equals to each other. Okay, so let's say here, the sine coefficient is a 3, cosine is a 3, regardless of the argument, it's 2t, but the coefficient is the same. So I know that this is a circle. Now this one, the coefficient for sine and cosine, the same. So I know again it's a circle. Before I start the graphing. For part E, once the coefficients are different, okay, so this is not a circle, it will be an ellipse. Okay, so this case will be an ellipse. Now we'll discuss them one by one, and the given domain is 1 full revolution, so from 0 to 2 pi. Let's just check with part A. Part A, they told me x from 2 sine of t, y equals 3 cosine of t. Remember, with all these questions, you can still use the table method. But what I'm using here is the elimination method. I need to eliminate t. So now for x, we know that sine of x equals to sine of t equals x over 2. And cosine of t equals y over 3. Now I'll use the trig identity, Pythagorean identity. Sine squared plus cosine squared of t, this is a fact, equals to 1. Just replace these values. This is x squared over 4 plus y squared over 9 equals to 1. And this is an equation of an ellipse. Okay, this is an ellipse. And how do we know the general form of the equation of an ellipse? Let's write it down. The general form, usually it's x minus a squared over let's call it alpha squared plus y minus b squared over beta squared equals to 1. Now these values here, a and b, are the center. Where's the center? Now alpha squared is, you think about it as, let's write it this way, easier for you maybe, that this is r of x squared, r of x squared, and this is r of y squared. So this is the radius over the x-axis, and this is like the radius over the y-axis. Now how do I graph it? Notice this one, the center is 0, 0. So we start from 0, 0. The x-axis, the radius from the x-axis, it's 4. So that's mean 2 to the right, 2 to the left. So 2 to the right, 2 to the left. This is with respect to x. Now I'll move to y. The denominator here is a 3. So which means we move 3 steps upward from the center and 3 steps down. Now the only task, we know it's an ellipse. We need just only to show the direction, the orientation. So to show the orientation, as we said before, we need only 2 points. Just try to take any 2 points within the given domain. Remember this question, the domain given here was from t from 0 to 2 pi. Okay, so I'll take 0 and I'll take pi over 2. I'll take usually quadrant angles. So this is x, this is y. If t is equals to 0, notice if t is equals to 0, x is 0. And y, if t is equals to 0, this is 3. So the first point is 0, 3, which is this one. Now the next point at pi over 2, we have it x as 2 and y 0. Okay, so let's see. So now we'll start plot. So we know we start from 0, 3. This is our starting point. And then we move to 2, 0, this point. So this way. We're moving this way. So the ellipse will look something like this. This way, we're coming down, we're going up, then we close it back. So the orientation will be clockwise. Okay, the orientation, this is an ellipse and the orientation is clockwise. You see, we didn't need the table for all. We just needed 2 points to double check the orientation. Now let's move to the second one, part B. This is the ellipse. Now in part B, notice that it's more busy, more crowded than before, but we'll follow the same technique exactly. So what I'll be doing, I'll come to this equation. Also, once you see sine, cosine, you know it's the same thing. It's a circle or an ellipse. It depends on the coefficients. So I have 4, 4. I know it will be a circle, but I need to solve for cosine and sine. The first equation, if you solve it for cosine, this is equals x minus 2 divided by 4. The second equation, if you solve it for sine, this is y minus 3 divided by 4. Again, I'm going to apply the Pythagorean identity. Plus cosine squared t equals to 1. This is x minus 2 squared divided by 16 plus y minus 3 squared over 16 equals to 1. Even though sine is y, but we usually write the x before. It's addition, so you can't just switch them, it's fine. Now this is the equation. So either I keep it this way or I write it this way. Both are fine, by the way. Both of them clearly an equation of a circle. This is 16. Now this is a circle equation, but this time the center is 2, 3, and the radius equals to 4. Now I'll come here. I need just to check the points. Center is 2, 3, 2, 1, 2, 3. This is the center. Now how do we plot the points? Remember, just it depends on the radius. So we need to move right, left, up, down, 4 steps, 4 units. So this is 4 units to the right, 1, 2, from the center. 1, 2, 3, 4. This is 1 point. Down 4 units, 1, 2, 3, 4. To the left, 4. Up 4. So this is all the surrounding of the circle. What's left here? Just to double check the orientation. It's always very important to find the orientation. And most of the time the question itself asks you to find the orientation. So if I take t, again, it's the same domain. It's from 0 to 2 pi. So I'll take 0 pi over 2. If it's 0, just help me to check. So if t is equals to 0, this is 4 plus 2, 6. And sine is 0, so this is a 3, 6, 3. So the first point, clearly 6, 3. This is our first point. This is our starting point. Okay, let's see the next one. Pi over 2. The cosine is 0, so this is 2. Pi over 2, it's 1, 4, 7, 2, 7. This one. So clearly we are moving this way. So the circle will be something like this. I'll try just to, we'll start from here. We move to there, down here, there, and here. So the orientation will look like counterclockwise. Please, you have always to add the arrows to show the orientation. This is the x-axis, y-axis. So the orientation in this case, is counterclockwise. Counterclockwise or anti-clockwise. Okay. So as you notice, all the questions involve sine and cosine. We always start with solving them with respect to solve for sine, solve for cosine, use Pythagorean identity. The equation will be either an ellipse or circle. How do we check? We look at the coefficient for sine and cosine. If the coefficients are the same, it's a circle. Different coefficient, it's an ellipse. And please remember always, when you graph, you start from the center. It's the easiest way to do the graph if you don't need to use the table. We start with the center and we move. If it's a circle, you move right, left, up, down, always R. Same like the radius. If it's an ellipse like the previous one, we start from the center and then we move. It depends on the denominator for x is the radius with the at the x-axis. So you move right, left, r of x, or 2 in this case, up, down, r of y, which is 3 in this case. Okay, let's see now the last one. Notice this is the circle, this is part C. What's the difference here in part C? This is exactly a circle. The coefficients are 3. Directly I can see it's a circle. But what will be different in this case? Why it's another question? If I start with our usual steps, let's see what will be different here. So I'll say that cosine 2 of t equals x over 3. Sine of 2t equals y over 3. Just apply. Remember Pythagorean identity, as long as they have the same angle, same argument, you can apply it. Cosine squared 2t equals to 1, which means that x squared over 9 plus y squared over 9 equals to 1. So this is x squared plus y squared equals to 9. So this is again a circle with center 0, 0 and radius of 3. Okay, center 0, 0, radius of 3. So if I compare this one with part A, or not part A, we have which question we did as a circle. Yeah, 1.3 was a circle, but that coefficient 2. Anyway, so this is again a circle, but what's the effect of that argument 2? Remember the given domain, the restricted domain, we have it before I graph. The domain was from t0 to 2 pi, okay? 0 to 2 pi. So if I'm graphing the circle with center 0, 0 and radius 3, these are the surrounding of the circle. And we'll graph the circle. I will check the orientation in a bit. This is x, y, and the orientation here, if you can check yourself for this question, then the orientation will be counterclockwise. Take any 2 points. The orientation is counterclockwise. Now, what's the effect of this 2t? If you think about the original domain t from 0 to 2 pi, now it's 2t. So you just adjust the domain times 2. So this is 0 to 4 pi. So what does it mean in this case? It means that this circle, the object traveled this circle twice. So the circle is okay. So we had the circle like 2 times. If it's 3t, that means we traverse the circle like 3 times. It depends on the domain. Originally, 1 revolution, 1 full circle from 0 to 2 pi. We have it here to 4 pi, that means it's twice. Okay, so this is the only difference in this case. Now, we'll move to different style of questions. The first few questions were only to graph the parametric equations, to graph the plane curve. Now we'll have different style of questions. They tell me, now we'll start, they give me something about the function, and we need to find the parametric equations. So the question is, we need to find parametric equations for the line segment joining 2 points. Remember, any 2 points, if you join them with a line segment, you get a linear equation. Now they give me 2 points, okay? And we join these 2 points with a line segment. They need the parametric equation. So what's required here is the parametric equations. Now, in general, the parametric equation for a line segment, it should be linear equation. Remember the general form for any linear equation, you write it as ax plus b. For any linear equation, it's ax plus b. But this is with respect, this is a parametric equation. This question can be done with different methods, different answers. It depends on your original assumption. So for me, we'll try one time. I'll show you 2 methods to do it. One method which I consider it much easier, and I'll show you the textbook method. The first method that I like to use is this one. I'll say in this method, since it's a line segment, okay, so I'll say let x of t, okay, let x of t equals to t, the parameter t, and y of t, it's the linear parameter, a t plus b, where t, remember these points are x1, y1, and this is x2, y2, 2. So x changes from 1 to 4. So if x is t, so that means t is changes from 1 to 4. Now this is my assumption. I assume that x is equals to the parameter t. So y, since it's a line segment, so it's a linear equation, I called it at plus b. And I define t from 1 to 4. How did I get this 1 to 4? Because t is x, and x is changes from 1 to 4. So I let t be changes from, or the restricted domain, from 1 to 4. Now the only task left for us is to find the values for a and b. To find the values for a and b. Okay, how can we find the values for a and b? We need to try. For the first point, for the point 1, 2. Okay, the first point we have it as 1, 2. If x is equal to 1, okay, as the first equation, So for sure t is equal to 1. Okay, and y is equal to 2. Now I'll plug this into this equation y. So we have hence y of t equals y of 1, okay, equals a plus b, and this is equals to 2. So a plus b equals to 2. This is my first equation. Remember always, if you need to find two variables, you need two equations. So the first equation, if x is equal to 1, remember this point is xy. This is xy. So if x is 1, so this means that t is 1 from the first equation. If this is x equals to 1, and we have y equals to 2. If I replace these two in the equation of y, so y, t is 1, substitute t1, and y is equal to 2, so a plus b equals to 2. I'll do the same thing for the second point. For the point 47. So for the point 47, this is x, this is y. So we have x equals to 4, y equals to 7, and this means that t is equal to 4. Okay, I'll plug it in the equation of y. So we have y of 4 equals, replace 4, so this is 4a plus b, and this is equals to 7. So 4a plus b equals to 7. Now I end up with these two equations, and with respect to a and b. Okay, I have these two equations. Remember your target. Our target is to solve for a and b. So I could solve these two equations by elimination, substitution method, any method you know for solving system of equations. So I'll use the elimination. So I'll do 4a plus b equals to 7. I'll subtract equation 2 minus 1. And a plus b equals to 2. I'll subtract these two equations. So I'll have 3a equals to 5, which means a equals 5 over 3. Now I need to find b. I'll do back substitution. b equals 2 minus a. Okay. And this is equals 2 minus 5 over 3. And this is equal, b equals to 1 over 3. Now we know the values for a and b. We're done. So hence, the parametric equations are x of t equals to t, y of t equals to 5 over 3, t plus 1 over 3, and t is between 1 to 4. So this is the first solution. I told you there's more than one. This is an easy one. Just only I assume x equals to t. It's a linear, so y equals at plus b. Another way where we can do it this way, this is method number 2. I need you to see that even different methods in the end, they represent the same line segment. Method number 2, they don't use x as only t, which could be always true. Remember that the idea just we're changing. We don't need only x and y. We need the equation to involve t. We need to introduce the parameter t. Now the other way is just to let x of t equals, it's a linear, so it's at plus b, and y of t equals ct plus d, let's say. And for this purpose, we need to define t from where to where. We have to do that. So I'll take, let's say, t from 0 to 1. I need to introduce t. Usually they use from 0 to 1. Okay, as t changes from 0 to 1. Now, according to this change, what will happen? We'll use this way. So this is the first case. So when t is equals to 0, okay, when t is equals to 0, corresponding to the first point, correspond to the starting point. Remember, it's an object moving. So we start from 0 to 1. We move from this point to this point. So the starting point of 1, 2. So now we know that t equals to 0 is related to the point 1, 2. Okay, why is this useful? So I'll come to this equation, x, I'll find x of 0. Okay, so this is equals to b. And this is equals, remember, this is x, this is y. So this is equals to 1. So now I know that b is equal to 1. Same way, if I come to y of 0, this is equals, if t is 0, so this is equals to d, and the y is equal to 2. So that means that d is equal to 2. So from the first point, I got b and d. Now I'll do the same thing with the other point, when the other value for t. When t is equals to 1, we take it correspond to the other point, 4, 7, the terminal point. Remember, this is x, this is y. We'll do the same thing. So x of 1 equals to, you come there, x of 1. Now remember here, what do we have x now? Our new values, we know b. So x of t equals at plus 1. From here, we know that y of t equals ct plus 2. Okay, so I'm building on these two. Okay, we replace x of 1. So this is a plus 1 equals to 4, which means a equals to 3. Now I replace y of 7, y of 1, sorry, still. Y of 1, this is equals, we replace here. So this is c plus 2 equals to y is 7. So this is implies that c equals to 5. Now we know all the values, so hence the parametric equations are the first equation, we have x of t equals, now a is a 3. So this is a 3t plus 1. Y of t equals 5t plus 2 for, remember how did we define t? From 0 to 1. Okay, from 0 to 1. Now if you think that this looks different than the previous solution, but in the end they are the same. If you take some values, you'll notice it's the same. So as a starting point, if you take t as 1, so t is, x is 1, and here try to 1, y is 2. So this is the point 1, 2. Try there at x 0. So this is 1, 2. You see, it's the same starting point. If you take 1, you'll get the same thing. So that's why there's more than one way to find the parametric equations. It's not unique. It depends how do you define t at the beginning. Okay, so here we use t from 0 to 1. You just get this from your head. Let's say that we choose 0 to 1. But in my previous solution, since I let x equals to t, so t is fixed. I can't use anything else. So t is just like x. It changes from 1 to 4, moving from 1 to 4. Okay, so this is the case of the line segment. Now let's move to another question. Now this is the easy one. We need to find, this is example 1.6. We need to find the parametric equations for the portion of the parabola y equals to x squared from -1, 1 to 3, 9. So it's a parabola, but with restricted domain. So it's not a complete parabola. We took only a portion of this parabola from the point -1, 1 to 3, 9. So this is simple. Remember, we need the parametric equation. So I need to introduce t. Parabola, we know the parabola is already given here. Y equals x squared. So I'll say what? Let x of t be, you can always start with this. X of t equals to t. Just replace x with t. Then y of t equals, now x is t. So I come here, this is not x squared now, this is t squared. For what should be the values for t? Notice that t is just like x, so it changes like x. So t is between -1 to 3. You see, very simple. The idea here, just we're introducing t. Okay, we're introducing t within this function with respect to x and y. So we have the functions only in terms of x and y, and we need to introduce the parameter t. The easiest way that I can see these cases, just let x equals to t. It's a parabola given, so y equals t squared. But remember, in these questions, you have to introduce the domain for t. So t here is from -1 to 3. Here, no need to graph it. It's only to find the parametric equation. The question asks us to find only the parametric equations. Okay? Okay. So now we have our last example for today. This is example number 1.7. It's again, we went back to sketching. Okay, so basically what we've done here in this section is either we sketch or we find the parametric equations. We need to sketch the plane curve of t, x equals t minus 1, y equals t squared minus 2. Okay, again, I'll use the idea of elimination. You can use, here they didn't give me any domain, okay? The question didn't introduce any domain. If there's no domain given, that means you need to find it for all of real numbers over its domain. There's no domain given. So now if I need to eliminate t, okay, I need to eliminate t. So I'll take the first equation, I'll solve for t. So x is equal to t minus 1. If I solve for t, this implies that t equals x plus 1. Now I substitute this value in the second equation in terms of y. So y is equal to t squared minus 2, which means that y is equal, now instead of t, I replace x plus 1. Don't forget to use bracket. X plus 1 squared minus 2. This is our function, which is a parabola, So this is x squared plus 1 minus 2. Remember, either you know the graph of this function or you use transformation, basic transformation. Remember that you're using you start with the parabola x squared. Okay, this is the parabola y equals x squared. And we have plus 1 inside, which means that we moved 1 unit to the left, and minus 2, which is 2 units down. So 2 units down, 1 unit to the left. 2 units down, 1 unit to the left. So the vertex here will be what? -1, -2. The vertex is -1. The vertex in this case of this parabola, -1, -2. So -1, -2 is the vertex of this parabola. And so let's just graph it roughly in this case and use another color. Okay. So we'll have this parabola. Okay. something like this. Notice that it's defined everywhere. It's defined everywhere. If I need to check the orientation, again, you can take always any 2 points. So t, x, y, you could take any 2 values for t, 0, 1, let's say. You'll notice that the orientation is this way. Okay. So this is the first graph, It's only a parabola. Now for part B, for the same question, this is easy one. Directly we know the parabola, we graphed it directly, no issues. Now with part B, this is the exact parabola, okay? And we're using for the graphing, again, we eliminate the parameter. Now, there's no restriction, as we said. The domain is the set of all real numbers, so there's no issues for t. We're going to use all t's. Now, the second part, part B, which is our last part here, you compare it with the previous one. Notice this is t squared, t power 4. The previous one was t squared. This is part A. I write part A in front of you here. Part A was t minus 1, y equals t squared minus 2. Okay, what's the difference here? In the previous question, the question didn't give me any restriction, nothing. There was no restriction in the question. Now, if I try to eliminate t here, let's see what will happen with us. I'm trying to eliminate t. Same thing as before. X equals t squared minus 1. Notice here I need t to the power of 4, so t squared is useful. No need to solve for t. T squared equals x plus 1. Now plug this into the other equation in terms of y. T to the power of 4 minus 2. I'll show you now where's the twist in here. So y is equal t power 4, which is t squared squared. So this is x plus 1 squared minus 2. So y is equal to x plus 1 squared minus 2. Okay, so is it going to be exactly the same graph? Is it going to be exactly the same graph? What do you think? What will be different than the first question? Think for a while. Just take a minute to think. Just compare to the previous one. Okay, I'll help you a little bit. In the first question, if we think about the t and x, here t was equal to x plus 1, which is a linear equation. This is defined everywhere. So x belongs to all real numbers and t belongs to all real numbers. We have no issues, no restriction. This is like real numbers, all real numbers defined. But if I think here about x equals t squared minus 1 and t squared equals x plus 1, okay? If I need this part here just to be defined, remember that t, if I need to think about t, it's equals to t, we take it only positive. So it's radical x plus 1. And this one to be defined, I need x to be greater than or equals to negative 1. I need x to be greater than or equals to negative 1. So I need this function only as x greater than negative 1. Remember the vertex was negative 1, negative 2. So if x should be greater than negative 1, so this is half of the parabola. So this is only the right half of the parabola. This is the right half of the parabola. Why it's the right half? Again, the question gave me no restriction, so I need to be careful about the restriction. So in general, there's no restriction. T can be anything. But if I think about x as t minus 1, so t is x plus 1, So this is like linear, it has no issues. X can be any value. So we could graph it from X with over all real numbers, like just the previous question. We graph the parabola over all real numbers. Now, in this part B, notice we have t squared equals x plus 1. Okay, t squared equals x plus 1. So if I solve for t equals radical x plus 1. So for this to be defined, since it's a radical, x should be greater than or equals negative 1. Remember, any square root, okay? To have any square root defined, we need a to be greater than or equals to 0. We can't accept negative values down. I'm talking about real numbers, okay? We're dealing with real numbers. So that means this is only the right hand side, the half of the parabola, only the right hand side, this part. So we'll graph only half of the parabola. Same orientation as before. It was this way. Okay. So as you see, with graphing plane curves, dealing with the parametric equations, we tend to do just the easiest way. We eliminate t, we end up with a function that we already know. It's a function in terms of x and y, which your whole life you were dealing with x and y only. So it's easier to graph. So this is section 9.1. Hopefully you like this section. Next time we'll do section 9.2, which is the calculus of these equations. We need to learn how to find their derivative. See you next time.